Okay, so now we're in Unit 2, 1 and 2 dimensional motion. This is going to be a really long unit, but the same physics topics kind of apply throughout the whole thing, even though we're kind of throwing in 2 chapters here. So I think we'll be all right. All right, so one-dimensional motion, one-dimensional kinematics just explains how objects move. When we study forces, dynamics, that'll be why objects move. But for now, we're just talking about like the distance, time, velocity, acceleration of certain objects. So first of all, of course, we're talking about motion in a line, one-dimensional, back and forth, or up and down. And we're considering objects that act as a point-like object. And throughout this class, we're going to make a handful of assumptions that, of course, aren't really true in the real world. We'll often ignore air. We'll often ignore friction. We know those things are always there, present in the real world. But we will consider objects to be a point-like mass. So even a car, obviously not a point, we'll consider that whole car acting as a point. Later in the year, we'll study rotational motion, and we will consider the size and shape and mass of like a tire, something that rotates. We won't just consider that to be a point anymore. We will take into account its shape. Okay, reference point. It's usually sort of just a given, kind of known thing, but it's just the point where the measurements are made from. If we're drawing something out in the coordinate system using vectors, we're usually going to make that the origin. So if I say the car is 10 meters east of the tree, obviously the tree is the reference point. And we saw this slide already, but just one more time. A scalar is a quantity where just magnitude is known. A vector, of course, also has a direction. So really this unit, we are still going to be talking about vectors for the most part. So direction matters. Often we'll just indicate like direction with a positive number for meaning forward or right or up, and a negative sign for left or down. But even though we're talking about just one line, we are going to be dealing with vectors. So our first vector, for instance, is position. And our textbook uses variable d. Different textbooks use different letters, but we're going to go with x for position. Just like you'd mark out the x coordinate of something. But don't forget there's direction along with that. So distance and direction from a reference point. And then displacement, which is this delta sign, Greek letter delta. And whenever you see that in science class, it always means a final minus an initial, second value minus the first value. So you can have delta lots of things. You can have delta t for time, delta capital T for temperature, but it means change in, and change in always means final minus initial. So for example, the car's initial position is 6 meters west of the tree. It's now 10 meters east of the tree. What was the car's displacement? All right, and then first assign positive and negative values to the directions. All right, well, what's its displacement? Here's my displacement formula. I want to do the final position or the second position minus the initial. So the final position is 10 meters east. Well, how do I deal with east and west when it says assign positive and negative values? Since this is just a straight line, of course, we'll make east positive and west negative. So that should be positive 10 minus 6. So that negative sign, that's for the west, which means the displacement was 16 meters. So you can try to picture that. 10 meters east of the tree, 6 meters west. Yeah, that entire displacement must have been 16 meters. And notice that it's positive. So really, since this is a vector answer, displacement is a vector, I should have a direction on there. Typically the positive would indicate east anyway, but it doesn't hurt to put the word east on there. Time interval, obvious. Sort of later, after chapter 2, kind of drop off the delta anyway. Time is just the amount of time from when our stopwatch begins. But the difference between two clock readings almost always start at time 0. And this is a kind of a common notation too. T with the little 0, subscript 0, that means T naught. Naught as in like nothing, 0. And we can see that, you know, V naught for velocity at time 0, etc. All right, average speed, average velocity. You know, in physical science, I often say these are pretty much the same thing, but here's your difference. Average speed is your total distance divided by the time it took you to do that, and it is not a vector. No direction matters here. Average velocity is a vector. It's also the slope on a position versus time graph. We're going to do a lot of graphing this unit as well. Sort of the same formula, but it's really displacement over time. Displacement over time. And so here are our units, meters per second. Here's a discussion question I think we're going to see later. Sort of a common, do you know the difference between these two things question is, a track athlete runs, you know, a 400-meter race. Runs 400 meters in basically a circle. And, you know, let's say it takes him 100 seconds to do that. 400 meters, 100 seconds. What is his speed? What is his velocity? Are they not just the same thing? Well, total distance, 400 meters, divided by time of 100 seconds, that would just be 4 meters per second. Okay, that would be the runner's speed. However, the velocity is not 4 meters per second. The average velocity is actually 0. We would say that runner had 0 velocity, because velocity is based on displacement. And displacement is based on where you ended up and where you started. And if you're this track athlete running 400 meters in a circle, your final position is the same thing as your initial position. So technically, your velocity there would be nothing. Okay, occasionally we'll have unit conversions, so don't forget dimensional analysis works for derived units too. If I have kilometers per second and I want meters per second, you know, I can just come up with a conversion for the kilometers to meters. Like I said, the big three, kilo, centi, milli. Kilo and milli are factors of 1,000. Of course, a kilo is bigger, so put 1,000 little meters with one kilometer. And you don't even need to worry about the seconds being here. That will just carry through. So, you know, your kilometers cancel, meters per second. You could add in some more fractions as needed if, for instance, you wanted to get rid of seconds and make that minutes. You could have times, you know, 60 seconds on the top, 1 minute on the bottom. But most likely we would be going into our standard metric units of 120 meters per second. Okay, and why I bother doing that right before this problem is that, you know, length, time, mass, units, they don't really matter what they are so long as they match. Now, we will almost always want to put things in our standard metric units. But wherever you see those fundamental units of, you know, length, time, mass, in your problem, they have to match. So even without reading this problem, right now I see I got 24 minutes and I have kilometers per hour. So right away, even though this is a velocity unit, kilometers per hour, I cannot deal with hours and minutes together. I've got to make sure my fundamental units match before starting a problem. Okay, so this is a problem out of the book. And I apparently threw in a question. Also tell what the displacement is. So it says a bus travels 280 kilometers south along a straight path with an average velocity of 88 kilometers per hour to the south. The bus then stops for 24 minutes. Then it travels 210 kilometers south with an average velocity of 75 kilometers per hour to the south. How long does the total trip last? Well, everything's south, so that's going to make this somewhat convenient for us. And then what is the average velocity for the whole trip? Okay, how long does the total trip last? Well, that's time. I can find my time sort of in each little part of this trip. I know that velocity is displacement over time. But I don't just have one velocity. So I can use this equation, but I've got to break it down into the 3 separate parts of this trip. And I'll get the 3 separate times of this trip. In fact, one of which I already know is 24 minutes. So let's just kind of write out, we got part 1, part 2, and part 3. And I usually like to write down the given info, sort of in a little list. Helps me keep all my terms straight, whatever I'm trying to solve for. So in part 1, the average velocity is 88 kilometers per hour. The displacement there says 280 kilometers south. And that leaves me with finding the time. So time is what I want. In this little section, the units match, kilometers, that's fine. I know my time answer will be in hours, since I was basing this off of kilometers per hour in the first place. So I will plug into, velocity is displacement over time. I'm going to struggle with room here. So I'm going to say 88 equals 280 over t. And I will not spend a lot of time in this class doing all the algebra and rearranging to solve for t. I expect you now to know how to solve for time. You got to get out the denominator first, divide by 88. So 280 divided by 88, 3.2, a little rounding. And that unit would be in hours. See if I highlight that. Okay, so there's one value I've found right now. The time is 3.2 hours just for the first part of the trip where I go 280 kilometers south. All right, part 2 of the trip. It says the bus stops. So I automatically know velocity was nothing, displacement was nothing, and the time it does give me is 24 minutes. But since these other values are based off of something per hour, it might make sense to change the one that's in minutes. And you can even change this all in seconds. It does not specify in the problem what unit I have to use. But I'm going to make my life a little easier and get rid of the minutes and make hours. So our conversion course minutes to hours, there are 60 minutes in 1 hour. So I would have to do 24 times 1, divide by 60. I get 0.4. Okay, so there's the next little piece of information I found. And now lastly, part 3, my given stuff. Bus travels 210 kilometers south, so that's the displacement. Velocity was 75 kilometers per hour. Displacement was 210 kilometers. Time, question mark. Okay, so once again, displacement over time, solve for the t. Basically 210 divided by 75. 2.8. Units there are still hours because, again, this was based off of kilometers per hour. All right, hopefully you can see that. Okay, so that was a lot of work. We've broken down all the information for each part of this trip. Still haven't got my final answer. How long does the total trip last? I want to do 3.2 plus 0.4 plus 2.8 to get my final answer. So that's going to give me 3.6, 6.4. Call that T tot for T total. Say 3.6, 6.4 hours. Okay, so the total trip takes 6.4 hours. What's the average velocity for the total trip? All right, displacement over time. Final position minus initial position. I'll assume the initial position was 0. To get the final position, though, I would just add up all of these displacements since they were all south, all in the same direction. So, sorry, I'm going to erase a little, let's make some room. It also says tell what the displacement is, so I'm going to need that anyway. Now, total displacement in this case equals 280 plus 0 plus 210. So that's my total displacement. Technically, I should say south, since it is a vector, need a direction. And last but not least, the average velocity for the whole trip would be 490 divided by the entire time, 6.4 hours. Kind of lost my units along the way, but I am dealing with kilometers per hour. 76.6. .6 kilometers per hour south. Good vector answer. Okay, moving on to another motion term, acceleration. You know what acceleration is? It's when you're speeding up or slowing down. It's the rate of change of velocity. So again, you see that delta V, which means final minus initial, or final minus, in this case, calling the initial the velocity when time is 0. Call that, again, V naught, all divided by time. Note that that could be a negative answer. Usually that means, of course, we're slowing down. Units are meters per second squared because, you know, velocity units are meters per second, and then you're dividing that by seconds again. So meters per second squared. A little harder to visualize. We know what a meter is. We know what a second is. But what in the world is a meter per second squared? Well, another way of reading it is a meter per second per second. It's like the velocity divided by time. Velocity is in meters per second divided by time per second. So if something's moving at 5 meters per second squared, it's just moving 5 meters per second faster per second. Moving 5 meters per second per second. So every time 1 second passes, this car is going to be going 5 meters per second faster. So velocity is obviously going up. It's going up at a nice, constant, steady rate. Our rate of acceleration is 5 meters per second squared. 5 meters per second per second. All right, so acceleration problem. Suppose a treadmill has an average acceleration of 4.7 times 10 to the negative 3 meters per second squared. How much does its speed change after 5 minutes? You know, technically we say that's change in velocity, but if everything is in the same direction, like it's not that example I gave you where someone's running in a circle, then it would also be change in speed. So really they're just asking to solve for this top part, but I should quickly list what I know, check my units. I know my acceleration rate is 4.7 times 10 to the negative 3 meters per second squared. I know my time is 5 minutes, and I want my change in velocity. In this case, same thing as change in speed. Problems, as far as my fundamental units are concerned, I've got seconds and minutes. Cannot put those into one equation together. Got to change one of them. Definitely going to be easier to change your minutes. 2 seconds, so 1 minute is 60 seconds. So that gives us 300 seconds. So now don't use the 5 minutes. Use your 300 seconds, plug on in, solve for delta V. And to get delta V by itself, I would just multiply that 300 over. All right, and I get just 1.41. 1.41 what? Okay, it's a velocity. Think velocity units. You need a length slash a time. Go with meters per second. Because that's what we based our formula off in the first place. All right, so that's part A. And since it just says speed, technically don't need a direction. Not that we really know what the direction is anyway for this treadmill. We don't know which way it's oriented. Okay, part B. If the treadmill's initial speed is 1.7 meters per second, what will its final speed be? So same given information. I don't want change in velocity anymore. I want final velocity, VF, is question mark. And now I also know this initial speed is 1.7. So call that, you know, V sub naught, V naught is meters per second. So let me highlight that again. So I know my, I know my acceleration, I know my time, and green is probably not the best choice there. I want my final velocity, I know my initial velocity. Basically plug it into the same formula, but now just break down your delta V into VF minus V naught. So solving for VF, you know, I pretty much do the same thing I had already done. And I already know the delta V is 1.41 on top anyway. So basically, what minus 1.7 is 1.4. So just add 1.7 to that. 311. All right, and there's your answer to part B. Okay, so now I claim we need more equations. What if we want the distance traveled while accelerating? Can we just use, our displacement over time as velocity formula? No. This is a constant velocity formula, or average velocity formula. So if you are accelerating, you have many different velocities. You can't just plug in one set velocity here, unless you know the average. But if we're accelerating, we're not going to use displacement over time to solve for our position. This is one of the most common mistakes in this class. If something says solve for the distance or solve for the displacement, this is a great, nice, easy equation to use. But if you're accelerating, you cannot use that equation unless you actually do know the average velocity. All right, but we can, of course, derive some more equations from this based off of this premise as well. How do we calculate the average of two numbers? Okay, if I have two test grades that are 90 and 100, I add them up divided by 2. So for average velocity, if you know your initial and final velocity, you could add them up divided by 2. That would be your average velocity. If I started at 50 miles per hour, I ended at 100 miles per hour, my average was 75. Assuming I had a steady rate of acceleration there, which we are assuming when we come up with these equations. So that's an average velocity equation. That's an average velocity equation. We're just going to stick them together and solve for position. And I will show you this one, although there, of course, is the answer. If I want to solve for, displacement, distance, all I've got to do is get that t to the other side. And the way it looks down here, we did kind of pull out that half. So pull out the half, multiply both sides by t. The t just gets stuck on the back, doesn't matter. Is delta x. So there is one equation we could use to solve for the position of a vehicle, car, person running, what have you, if they are accelerating. But again, accelerating at a constant rate. And we're not dealing with calculus here, so we are going to be dealing with a steady, set pace, no changing accelerations here. And this little list of equations is called the kinematic equations. We will use them all year long. They're sort of your motion equations, how we describe how things are moving. They have everything we've gone over so far in them: velocity, acceleration, time, and displacement. We don't usually put the F for final on this V, but it does mean final velocity. And again, V naught means the first velocity when we start our stopwatch at time 0. Number 4, we don't really use that much, but technically does exist as a kinematic. And this last one here, where there are squared values, I do want you to note, if, for example, you're solving for the final velocity of a car, the last thing you would do if you want to solve for V is square root everything. Well, if you're going to square root everything, you're going to get a positive value, regardless. But depending on your problem, maybe your final velocity is negative. I mean, maybe this was something moving to the south, or moving west. So be careful there. You may have to add your own negative sign on your answer just for this equation here with the squares. So these again are called the kinematic equations, really the fundamental physics equations for describing motion when something is accelerating, when there's a constant acceleration. If there's no acceleration, perfectly welcome to use displacement over time. Okay, so we had all those equations. How do you know which one to use? Well, like we sort of started doing already, when you're given a word problem, list what you know and list what you want. These are going to be the variables that pertain to the kinematics: displacement, time, initial velocity, final velocity, acceleration. And just pick the equation that has those variables in it. Make sure units match, and check for positive and negative signs. Make sure those are correct. Something says it's going backwards, and you've made forwards positive, you need a negative sign. And then solve. So the kinematics really pretty easy once you get the hang of it. Just really helps to list what you want and what you know. So a motorboat accelerates uniformly from a velocity of 6.5 meters per second to the west to a velocity of 1.5 meters per second to the west. If its acceleration was 2.7 meters per second squared to the east, how far did it travel during the acceleration? Okay, so I see the word acceleration in a couple places. I know this has got to be a kinematics type problem. But just listing, first, what is it I even want? How far did it travel during the acceleration? Okay, how far? You're thinking distance, displacement. That's the variable delta x. That's what I'm looking for. Now I just start pulling out any numbers. All right, I see 6.5 meters per second west. That's a velocity. Now, is that initial or is that final? I do need to be careful when I note that. It says from 6.5 to 1.5. So they're both velocities, but if it's starting with a 6.5, that's the initial. I'll put the little v naught there. Now, they're also both west, so I'm going to call those negatives. Negative 6.5, negative 1.5. Lastly, its acceleration is 2.7 meters per second squared east. Okay, so east, that's going to be positive. I'm just going to leave that at 2.7. That is the A, that's the acceleration. There we go. Okay, so now I've got what I want, I got what I know. I don't have any unit issues, that's fine. All the fundamentals are in meters for length and seconds for time. So that's perfect, nothing to change there. I just have to pick an equation that has all of these things in it. And sometimes the easiest way to do that is to just figure out what you don't have and find the equation that doesn't have that thing. So I don't have time. That's the last little kinematics variable I would possibly have. I don't have time. So the only equation that doesn't have time in it is that squared one that was last. So that's the equation I want to plug into. It is just plug and chug now. Even though these are negative values, it's not really going to matter in the end because I'm squaring them. But .7. All right, you take a second to see if you can work out what delta x is. I will do the same. So I get 7.4 meters. I put meters on there because, again, that was the fundamental unit I started with for length. I do get negative, so either leave it as negative 7.4 meters, but perhaps better to write out west since the problem did originally give you directions like east and west. So 7.4 meters to the west. Certainly makes sense that this boat is still moving to the west. Its final velocity is 1.5 meters per second west, so it's still going west. It's slowing down, but it's slowing down while moving west. All right, and that's how you attack a kinematics problem. Okay, now we're going to throw in probably the most common acceleration we'll use this year, gravity. Gravity is a natural acceleration. Depends on the mass of the two objects, so typically we're talking about something being pulled down towards the Earth. But we can talk about gravity between any two objects, and we will later in the year talk about the moon, the sun, planets, satellites, things like that, not just objects falling to the Earth. But we all know gravity makes things fall, and here on Earth, gravity is 9.81 meters per second squared. That is assuming we are close to the surface of the Earth. Negative, of course, means down. So we will use this number a lot, but it doesn't mean that number will even ever be given in a problem. If you're told in a problem that something is falling, then definitely gravity is making it fall. Or if something was dropped, gravity made it fall as soon as you let it go. So keywords, something's falling or dropped. Gravity is negative 9.81 meters per second squared. Dropped, okay, gravity applies, and the initial velocity is 0. Okay, yeah, this pen is about to go faster and faster and faster, but at the very top there, its initial velocity is nothing. And then just watch out for signs. If you're talking about something falling, its displacement is down. So you'd want a negative value there for displacement. All right, so let's do another kinematics problem, but this time with gravity. It says a flower pot falls from a windowsill 25 meters above the sidewalk. All right? It says falls right there. I know gravity applies. How fast is the flower pot moving when it strikes the ground? All right, how fast is it moving? That's a velocity question. I want the final velocity. I know it's falling, so I know gravity is 9.81 meters per second squared with my negative. Okay, it started 25 meters above the sidewalk. So that's displacement, although this time rather than writing delta x, I'm going to write delta y, since that's sort of vertical information. Doesn't really matter. But then since it's going down, I want to make this a negative displacement. Because really my final position is 0. My initial position was 25. Final minus initial, 0 minus 25, so give me that negative. And then what else? Okay. I do need one more term, and this doesn't really say dropped, but it also doesn't say that the flower pot was like thrown down. So you are supposed to assume in this problem that the initial velocity is nothing, is 0. So it just fell out the window, it wasn't thrown out the window. All right, so that's all the info we've got. I look through my kinematics to find one that has these variables. Actually, it's going to be the same one we just used. Although this time we're solving for something different, but v squared equals v naught squared. I'll change it to delta y. And right here, you're going to have a negative times a negative, so that will be positive, and then you're going to square root that. So if you are ever trying to square root a negative number, you've forgotten a sign somewhere. That should not happen. We should never be trying to take the square root of something that's negative. All right, so you can try, I will try. see what we get there. Okay, so the final velocity I get is 22.15 meters per second. Really, that's a speed answer. To make that a velocity, I should either write the word down or put a negative sign on there. But it just says how fast is it moving, so it's sort of a magnitude question. I don't really care what the direction is, and obviously the direction can be down anyway. But it is moving at 22.15 meters per second when it hits the ground. Second question, how much time does a passerby on the sidewalk below have to move out of the way before the flower pot hits the ground? Okay, so now I want to add t to my unknown list, and I want to solve for time. At this point, since you know the final velocity, you could use any of the kinematics. But since this was something we just came up with, we calculated this ourselves, just in case we messed that up, I'd like to not use that if possible. So I'm just going to give myself a little room. So now I want an equation that's got A, delta x slash delta y, v naught, and t. And that would be this one. All right, so plug it in. And we got a little lucky here earlier. I was afraid of using this equation for a second just because t is in two places. So we got lucky because the initial velocity is 0. I say that because now I don't care about that term. If the initial velocity was not 0, this would be a pretty annoying turn into a quadratic function using the quadratic equation to solve for this kind of problem. And we will do that a little later in WebQuest in this unit. Pretty rarely do we bust out the quadratic equation, but in this case, no big deal. I got my correct negative signs on there, so negatives won't matter. Sort of divide by 4.905 and square root. So solve for t. I will do the same. And I get 2.26 seconds. And that seems reasonable. I mean, it's 25 meters above the ground to begin with. Try to make sense. Try to make sure your answers seem reasonable. We know in real life with air resistance that wouldn't exactly be the right time. But it's certainly not like 200 seconds. That's a reasonable answer. Okay, so we've done one-dimensional kinematics, and now we're going to apply those same terms, velocity, displacement, acceleration, to some graphs. And we've mentioned velocity and average velocity. Here would be a case where your velocity is definitely changing, and it's not even changing at a constant rate. But the instantaneous velocity is a slope on a distance time graph. And slope for a curvy line is what we call a spot that would be tangent to that line. And we would use calculus to find that. So fortunately, we will not really deal with curvy lines. We'll deal with lines that are a little more steady. But certainly acceleration doesn't have to be constant. Constant velocity would be a constant slope. So clearly a constant slope right there as the distance is increasing at a nice steady pace. Okay, so we mentioned velocity is slope. Well, remember your equation for a line, y equals mx plus b. If we ignore b, the slope part of that, the m, will be y divided by x. And in this class, you know, with some of the labs that we do, we will often graph things, and the slope will often have some physical meaning to us. I know in math, you know, you're just kind of plugging in numbers, but now they will have some physical meaning. So applying that to, you know, velocity of displacement over time, this equation is set up just like that equation. So I could say slope must be velocity. On the y-axis, I would have to put displacement. On the x-axis, I'd have to put time. And if that were set up that way, slope is velocity. So we will study those three types of graphs: distance, velocity, acceleration. And I'll ask you questions about those three things: distance, velocity, acceleration on each graph. With the exception that I won't start you with a distance graph and ask for acceleration. Or at least it will be 0. Okay, so here's a distance graph. If you are asked distance questions from a distance graph, you know, that should be a piece of cake. Just look at the graph. You know, what's the distance at 1 second? Okay, I traveled 3 meters. What's the distance at 5 seconds? 6 meters. 7 seconds. 3 meters. Okay, distance graph, distance question, easy, just look at it. Same for velocity graph, velocity question, easy, just look at it. Acceleration graph, acceleration question, easy, just look at it. All right, but what if I change this to velocity? How do I get velocity at these spots? Well, it's slope. So you guys just have to remember from your math class how to get slope. And to get slope, you just pick 2 points on the line. But you know, not just any point. So this says velocity at 1 second, and I would just go ahead and use 1 second. I can pick that point, but you can't come way over here and pick this point, because this is part of a totally different slope than the beginning was. So I can pick that point, and if you can, pick 0, 0. I can pick that point, slope, rise over run. So I go up 3 over 1. 3 over 1, 3. Velocity at 5 seconds. Make this easy on yourself. This is a flat line. So my distance went up and up and up and up and up. I reached 6 meters, and then it stayed at 6 meters, stayed at 6 meters, stayed at 6 meters. So this person walking, or car, or whatever it is no longer moving. And just recognize flat line, you know, there's no slope there. All right, lastly, at 7 seconds, I can pick that point. Again, whatever point you want, but it needs to be on the little line segment we're talking about. It needs to have this slope. So pick the end point. That's sort of the opposite of that. Down 3 over 1. So if I go down 3 over 1, that's really negative 3 divided by 1. So negative 3 meters per second. Now take a second and just look at this graph, because there is an unrealistic part of it. You know, in the beginning, we're moving at a nice steady velocity, 3 meters per second, moving along, moving along. But at 2 seconds, we just automatically stop? No. You know, there's no way to go from 3 to 0 instantaneously. You know, we got to go to 2 to 1 to 0. And that might happen extremely quickly, but it still is going to take some time to happen. So I've made these graphs look this way just for the ease of the math and the slope. But I do want you to realize that this should be, you know, curved. There definitely is a slowdown or a negative acceleration right here. Likewise, you can't go from stop to automatically moving negative 3 meters per second. And we're, I guess, thrown it in reverse in this case, backing up. So there's a little acceleration here. We're accelerating backwards. But it would be curved. So any of these graphs where you have the sharp points or the cusps doesn't really exist in the physical world. Just did it to make the math easy. Okay, so let's move on to another type of graph, a velocity graph. This looks exactly the same as the graph we just did. Goes up, it's flat, goes back down. Totally different story though. It's a velocity graph this time. So I'm not saying my distance goes up and up and up, although it does, but my velocity is going faster and faster and faster and faster and faster. And then I don't stop. Flat line doesn't always mean stop, depends on what type of graph it is. Then I just kind of coast. So we got a constant velocity of 4 meters per second. And then I do slow down. My velocity goes back down all the way to 0. And I do stop here because my velocity is at 0 again. But this shape means a different thing on a velocity graph. So be careful of what type of graph you're looking at. Okay, so I'm asking velocity questions this time around. On a velocity graph, like I said, that's the easiest thing I could ask you. Just read the graph. At 1 second, we're traveling 2 meters per second. Oh, I lost my pen. At 4, that's 7, 2. But what if I ask for acceleration? Okay, so acceleration is also slope on a velocity graph. So just like, you know, y equals mx plus b, we can say the slope is y over x. That also fits this equation too, velocity over time. So slope at 1 second, you know, pick 2 points, I go up 2 over 1. Don't forget your little squared for acceleration. 4 seconds, all right, that's a totally different line segment, that's right here. Flat line, 0 slope. And 7 seconds. So I can pick this point, I can pick my end point, down 2 over 1, negative 2. All right, now on a velocity graph, we can also ask distance information, and we can get that from area under the curve, which is another calculus term that's really integration. But area under the curve of, you know, nothing with the curve is easy to do. As long as we know how to do area of like a square, area of a triangle, we should be fine. But again, this is a velocity graph. We can get position by doing velocity times time. But you got to be a little careful, of course, because, you know, it's not like I just pick one velocity, because it's an ever-changing velocity. You know, my velocity is ever changing. I still, though, have the idea of velocity times time. This side times this side. That's sort of the area idea. Length times width. So the distance at 1 second, you got to mark off your 1 second. Area under the curve means draw a line from wherever that point is to the x-axis. This could have been from the negative direction straight up, but in this case, we're going to go straight down and all the way back to the beginning of time. If I want to know the distance I traveled since time was 0, well, we got to start at 0. Basically, I need to find this little bitty area. I need to find the area under the curve right there. And that looks like a nice little triangle. So it really helps if you know your triangle area. Where a triangle is half base times height. So base is 1, height is 2. 1 times 2 is 2. Half of that gets me back to 1. 1 meter. All right, distance at 4 seconds. Let me erase this. At 4 seconds, okay, so there's my line, my graph. Draw straight to the x-axis, straight down. So I need to know all this area. Well, break it into shapes that you know. You got a rectangle here. And you got a triangle here. So you got 2 little area chunks. Rectangle, let's see, length times width. So we got sort of a length of 4, or height of 4. Width, though, is not 4. It's just 2. Up 4, over 2 for the blue part. So that's an area of 8. And then this should be half of that, but triangle, half base times height. Base is 2, height is 4, that's 8, but half, so 4. So I just did the area of a triangle, area of a rectangle, add that all up to get the total distance we traveled at 4 seconds, be 12 meters. And now we got to do that one more time for 7 seconds. So I'm going to erase the blue. I'll keep this red triangle, though. I still kind of need that. I'm just going to expand my rectangle. So 7 seconds, that's right here. So I know this makes a nice little triangle, but I don't need that. I need everything up to the 7 seconds. So you got to be a little clever about how you make your shapes. There's different ways you can do this. I'm going to make one big rectangle in the middle. That is 4 up. 2 to 6 is 4 over. 4 times 4, so that's 16. And then I just need this green chunk to add into that as well. Or you could have found like the big triangle, subtracted the little triangle. I'm going to say I've got this bottom green rectangle with a little base of 1, height of 2. That's 2. And I've got this top little bitty triangle. Again, half base times height. Base is 1, height is 2, half of that, 2, 1, sorry. So all my little area bits add up to 4 plus 16 plus 1 plus 2. So that's 20, 23. So that is the total distance traveled at 7 seconds. Note that we would definitely have been wrong if we had just said, okay, it's velocity times time. I'll just pick 7 and the 2 that matches there and say it's 2 times 7 is 14. No. And again, the reason you can't just do that is because you have a constantly changing velocity. We never use this when we are accelerating. Okay, and the last type of graph we'll see this unit is an acceleration graph. So we're just looking at 3 graphs, distance being the most basic. You divide distance by time, you get velocity. If you divide velocity by time, you get acceleration. So acceleration graphs for us will actually look the simplest because we are either going to deal with a set acceleration of something or no acceleration. So we will pretty much have these little step functions. Again, in real life, I can't go from acceleration of 4 meters per second squared instantly to nothing. Yes, it would kind of curve out a little bit. But our acceleration graphs will always just be flat lines. So if you have acceleration graph, acceleration questions are pretty easy. Just read it. The acceleration at 1 second is 4 meters per second squared. 5 seconds is nothing. 8 seconds is nothing. Just read it. We won't go past this to do slope, but we could sort of go backwards. What's the velocity at certain times? Now, I do need to assume that I started at rest, though. This will only tell me how much my velocity increased or decreased from the beginning. But assuming we're at rest, I can still do area under the curve to get these velocities. And at least these areas will be easy. Flat lines, we're just going to have little rectangles. So at 1 second, go to your graph at 1 second, it's right there. Draw a line straight to the x-axis. So area under the curve is all the area from time 0 up to that point, under the curve. So up 4 over 1, that is 4 meters per second. So assuming I started at rest, after 1 second, I'm going 4 meters per second. Should make sense, my acceleration rate's 4. All right, at 5 seconds. All right, well 5 seconds actually is flat. So there isn't any area here, but there is area under the curve up until 4 seconds. So I'm still adding up all the area to get me over to 5 seconds. Yeah, that little chunk's nothing, but I do need to do 4 times 4 and get this chunk of 16. This car accelerated all the way up to 16 meters per second, and then again, it's not that it stopped, it just stopped accelerating. So now it's staying at 16 meters per second, staying at 16 meters per second. So it should be the same story for 8 seconds. All of this is 0 area, but the car still reached 16 meters per second before the acceleration dropped to 0. All right, so pulling information out of graphs is all about area under the curve, just reading it, or slope. And here are sort of the trends. Like I said, we're only going to deal with these 3 graphs. You can call it position, distance, displacement, pretty much the same thing. Velocity, acceleration. If you are given, say, a position graph, slope always gets you sort of 1 step more complicated. So if I'm given position, the slope of that would be velocity. If I was given velocity, the slope of that would be acceleration. Backwards is area. If I'm given acceleration graph, the area under the curve is velocity. If I'm given a velocity graph, the area under the curve is position. It also helps, of course, to think about what this graph actually represents. Try to imagine it's a car, person walking, and what they're doing. Note times where the motion changes. Recall what we know about slope and area. And we didn't draw one of these or see one of these, but acceleration is apparent in a curve on a distance graph, because if it were a constant velocity on a distance graph, you'd have a constant slope. Well, what if the velocity is increasing, increasing, increasing? Well, the slope should be increasing, increasing, increasing. So hard to draw that without knowing a little calculus, but at least recognize that it is curved. That's speeding up, slowing down. The slope is getting less and less and less. So I do want you to be able to draw from graph to graph. Draw based off of one graph what the other two might look like. So we're going to try to spread this out. Get a pen. So this is the velocity graph. It's kind of like the middle graph. But we also have position. And acceleration. And so note times of change. You don't need to mark every single time on there, but if something changes, mark it. So something changed at 4 seconds. And of course, it ends at 8 seconds. So I'm going to mark that off. 4 and 8 on each of these. 4 and 8. And I'm also just going to try to imagine what is actually happening. If this is a person walking or running, what are they doing? All right, well, this graph tells me their velocity is 4 meters per second. Okay, so they're moving. They're moving at 4 meters per second. Still 4 meters per second. Still 4 meters per second. So they got a nice steady pace right here. At 4 seconds, they start to slow down. Their velocity is going down and down and down and down until they actually stop. So just from kind of thinking through that, I already know there's no acceleration for 4 seconds. We're moving at a nice steady pace for 4 seconds. I'm not speeding up. I'm not slowing down. So there's no rate of acceleration there. I probably should make this negative, sorry. To finish my acceleration graph, though, I need to know slope. So the slope of that last little line segment, I go down 4 over 4. Down 4 over 4. So that's negative 4. I mean negative 1. And like I said, acceleration graphs for us are just going to be flat lines, little step functions. So this entire time, the acceleration is negative 1. Yes, real life, kind of curve it out a little bit, but that is our acceleration graph. Done. So I knew velocity, I wanted acceleration, I did slope. Now I'm going back the other way. I know velocity, I want more basic, I want position. So I need area under the curve. So we've got our times of change marked out. So we'll just start with 4 seconds. All this area is 16. So I kind of put a little point there. I know at 4 seconds, my position is 16. How did I get there, though? Do I just connect from 0? Is it flat? Is it curved? Well, are you accelerating or not? If there's no acceleration, there's no curve. So I just need a nice steady increase to 4 seconds. All right, 4 to 8, continue with your area. Remember, this chunk was 16, so I still need all the area. This triangle, all right, base is 4, height is 4, half of 16 is 8, so all of my area is 24. So let's see, we got 8, 16, 24, something like that. And these graphs will look better if you have a decent little scale here. You know, trying to say, okay, maybe that's 8. Every little chunk's 8, 8, 8. But if you're just marking off numbers willy-nilly without a sense of scale, it's going to look weird. So I'll now mark off 24 meters at 8 seconds. How do I connect this? This is not going to be just a direct connection. because I do have acceleration. If you have anything at all for acceleration, there's going to be a curve on the position graph. So now, which way do I curve it? Well, I'm slowing down. My velocity is going down, 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 down. So my slope here should be going down, 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 down. This should be becoming more and more shallow. And it should look kind of smooth, too. I should be able to go from this line right into this line. So something like that. So constant, slowing down. And that's how you draw from one graph to the other. All three of these graphs tell the same story about a runner going at a steady pace who then slows down and stops. But describing motion with positive and negative signs, I probably have already said a few times. Negative acceleration means you're slowing down. Not always. Usually. Not always. How we know if you're speeding up or slowing down depends on the signs of the velocity and the acceleration at a certain moment. So if you have a positive velocity, let's say just make up this little reference frame talking about this car. This car could be going left or right. If you have a positive velocity, it would mean it's going right. So it's moving away from the tree, to the right. And the acceleration matches. That's kind of key. If it matches in sign, it's going faster and faster and faster. And if I were to graph that as a velocity graph, I'm starting with some positive value, and I'm accelerating, going faster and faster. So my graph would go up. Vice versa, if I had negative velocity, negative acceleration, that still matches. I'm still going faster and faster here. So here's a case where negative acceleration doesn't mean you're slowing down. You're just going faster and faster in the negative direction. So I was already going towards the tree. I was already going left. And now I'm going faster and faster left. So that graph would look like that. Sorry, I'm kind of running these into each other. When the signs don't match, that's when you're slowing down. So for the car case, positive velocity, okay, it's going to the right. Negative acceleration, it's almost like it wants to go left. Maybe it will, maybe it won't. But it's going to the right, but slowing down. So it did start with a positive velocity, so I do need to start my velocity graph up here, but it's going to slow down until it stops. Negative velocity, positive acceleration starts out going negative left. So negative, start my velocity down there. But it's slowing down until it reaches a velocity of 0. Okay. All right, last slide for the day. So one more time, if the velocity and acceleration have the same sign, you're going faster and faster, speeding up. But if there's opposite signs, that's when the object slows down. And the car example can only slow down and stop. If it's a braking force, that's only going to stop the car. But maybe try to imagine a runner running against a humongous rubber band or a bungee cord or something. So they're running, maybe positive velocity, negative acceleration, that rubber band's trying to pull them back the other way. At a certain point, that runner is going to stop, and if that force from the rubber band is constant, which it wouldn't really be, but it would pull the runner back the other way. So given enough time, that object would stop, and then the velocity would reverse direction. Your acceleration rate staying the same the entire time, but your velocity would change to match the sign of the acceleration. So If they're opposite signs, you're slowing down. Given enough time, that object would perhaps stop and even reverse direction. Just depends on what that force is that's making that happen. All right, the end for today.